Hello, everybody. Welcome back. In this lesson, we will go over the next computational aspect in calculus. Up to this point, we learned how to take derivatives of given functions. Starting from this point, we will consider the reverse process of differentiation. This is in fact is leading to the second most important branch in calculus. First, we learned about differentiation, and we learned differentiation, or in other words, the derivative, gives the slope of a given graph. That was a mathematical breakthrough. The other variation or the other important aspect in calculus is associated with the term integration or integrals. And integrals, eventually, when we consider a refined version of integrals, which is called definite integrals, we will get to know it will represent another geometric aspect, which is known to be the area under a given graph. However, before getting to that particular geometric application, we need to understand the computational layer. So that starts simply with the process of antiderivatives, so process of finding antiderivatives. That process is called antidifferentiation. So what is an antiderivative? So there are two technical terms that we're going to learn in this journey: antiderivatives and indefinite integrals. But computationally, you will understand both of these are exactly the same. The only difference is antiderivatives and indefinite integrals, those two are notationally different when we indicate them. But just try to understand, we will use antiderivatives and indefinite integrals interchangeably in our applications. So what is antidifferentiation? The process of finding the reverse process of differentiation, in other words. What do we mean by the reverse process of differentiation? Simply think about when the derivative, if you consider the derivative, if the derivative is already given, when the derivative is given, we need to find the original function where it is coming from. We need to find which origin gave us that derivative. So in other words, precisely in mathematical forms. Now, when we work in mathematics, we need to have precise definitions. Now, what is the definition of antiderivative? An antiderivative is simply like uppercase f of x is defined to be an antiderivative. So this guy, this particular function is an antiderivative of this given function. This is the original. So when the original function lowercase f of x is given, the uppercase f of x is the function that we need to find. In other words, we need to find this, need to find the uppercase f of x. The original function is given. The connection between the given original function f of x and the function that we are finding would be when the derivative of our finding, uppercase f of x, this function, when the derivative of this uppercase f function is computed, f prime here, that should coincide with the original function. So there is always a simple computational way to verify your answers in this section. And at the same time, you can consider this particular section as like being familiar with the forward derivative computation. That simply means you know how to compute the derivative. So this is just like walking backwards. You try to backtrack, you try to find where that derivative or where that answer came from. However, other than having this ambiguity in our communication, we can prepare some notation to deal with it. So bear with me and you will see exactly how it is done. Example number 1. Now, just based on exactly the definition that you're given. Now here, look at this. The the derivative of a certain function, f prime, is given. It equals this. What we need to find is the original function. This is exactly working backwards to figure out the original function. So in other words, what we do is to find the antiderivative of this function to get rid of this derivative operation. So the answer is pretty simple in this scenario. All you need to do is to recognize whose derivative is going to be each of these individual component. So the will familiarity with derivatives will be the key for all of these computations. So f of x, let me just write it, 4x cubed. Now think about your differentiation. When you consider derivatives, which function, when you differentiate, would result 4x cubed? If you're not, if you do not recall it, now, now think carefully, and do the same process with each and every individual function here. Give it a try if you can write it. If not, uh, have a pause this video and make sure that you attempt this first. All right. So when you consider 4x cubed, that is exactly coming from x to the fourth. If you differentiate x to the fourth, we know it will be just 4x to the third. And then we know the derivative of sine x, that would coincide with cosine x. So the answer that I need to write here is sine x as the antiderivative of cosine x. And then when you consider this component, we know there's a constant multiple, and we know in differentiation process, constant multiples are not going to disturb us. So 5 times whose derivative will be ex, that will be just ex itself. And then minus, here you have 7 times. You can write this one in a different form if you would like to see it in that way. Minus 7 times 1 over x, whose derivative would be 1 over x. That's what you need to recognize. So the answer here is going to be 7 times. We know 1 over x is generated by ln of x. Now here in this case, when we work backwards to make our answer more general, we will have ln of absolute value of x, and we will see that in upcoming computations when we develop formulas, because that's just about extending the domain of applicability of this function or this formula. And then once you're done, you may have a feeling of like conclusion, oh, we covered all of these terms. However, there's another component that you need to pay attention to. What is it? Now, pretend that you had something completely different here, like let's say you had all of these functions, and apart from that, you had plus 100. Now, if you had that kind of a constant, 100 is a constant, right? So when you take the derivative of that constant, now if you check back from here to there, each term would match with each derivative and everything checks out, right? But then when you consider 100, of course 100 will cancel. It's a simply, it is none other than just a constant, so that should disappear, so it's not actually getting associated. And then when you give it another thought, it need not to be 100. You can see it could be any constant. If you have 7, -5, pi is a constant, right? Or e, just e itself, it's a constant. If you put any constant here, it's gonna simply disappear when you take the derivative. So that simply tells us the indefinite nature of our answer, because there will be a constant, and that constant can be that constant is going to be an arbitrary constant. It need not to be any specific value. So I will indicate it by always, like usually by plus c. This is an arbitrary constant. So the role of this arbitrary constant is just, it is not uh, getting uh, any specific value. In other words, this entire function actually not a function. It is not a function. What you have is a family of functions. So when you consider this inverse problem, it does not allow you to have just a single function. It will represent a family of functions. How many in that family? There are infinitely many uh, number of functions in that. All right. So keep that in mind. In anti-differentiation problems, except for very specific situations where you have initial conditions, you're going to have always this plus c, which is going to stand for an arbitrary constant. All right, so let's proceed to the next example. Example number 2. Let's proceed with the same method. Now here, find the antiderivative of function f of x. In other words, here, this is not f prime given and find original function f. Here we are saying f of x is given, then find the antiderivative. That simply means now I'm going to write down uppercase f of x. The goal is to write down this function in a way, when you take the derivative of that function, that should result exactly what we have there. And don't forget that family of functions, at the end you need to have plus c. So this is easy. 3x squared would be a result of x cubed minus 2 times secant square is coming from tangent. So when you differentiate tangent x, you get secant square. And then 1 over 1 plus x square is none other than arctan x. And then don't forget plus c, which is our arbitrary constant of the computation. So do you see, when you're fluent with derivative computations, these computations are going to be essentially simple. However, soon enough we will define a bunch of formulas for indefinite integrals. Indefinite integrals, in other words, the antiderivatives. We will have formulas, but before getting to the formula level, uh, you can see already you can compute most of this by the basic familiarity with differentiation process. All right, extra example. Now here, let's consider this situation. Find the antiderivative of this function. I will write first of all uppercase f of x to indicate uh, the antiderivative of a lowercase f. Now you need to find a function whose derivative is going to be just x square. Now if you have 3 here, 3x square, we know what it would be. It's going to be just x cubed. However, when you have just x square, how is it going to work? The answer is essentially associated with x cubed yet. So this is what I'm going to do. When you have a constant multiple in front, it is not getting involved with these computations. So let me have 1/3. I will just, by inspection, I'm going to put it right there. And then I'm going to write x cubed. Now think about this. What happens if you take the derivative of this component? You will have 1/3 in front, and then you will introduce 3x square because you're taking the derivative of this. These two will cancel with each other, leaving just x square. And that will lead to just x square right here. That's exactly what it is. So always when there's a mismatch with constants, you can easily play with that. And then minus 3. Now the derivative of sine x is going to be cosine x. That's correct. However, when the derivative of cosine will, when you have the derivative of cosine, that will introduce negative sine x. So when you compute the integral, or the reverse of the sine is none other than reverse, or the antiderivative of sine is none other than negative cosine x. Now, if you do not see this fact, I recommend you to think again in this way. Take the derivative and see. Now, in the next step, you can see, you can just put them together and make it just plus cosine x. So let me do it right now. So I will just put that plus sign here and then cosine x. And then secant tangent is none other than a result of secant x. The antiderivative of secant tangent is secant. Then plus c is our arbitrary constant, the placeholder for a constant. All right, so let's look at the one instance, one occasion, we will have a chance to get rid of that plus c, the arbitrary constant. First of all, this kind of a problem is called an initial value problem. How can you recognize it? It has a derivative. First of all, the derivative is given. And then there is an additional condition called an initial condition. Initial condition. The purpose of this initial condition is to give an extra opportunity for us to evaluate that constant plus c at the end. So first of all, our first step in our answer process is to have the original function out of this. Of course, it's not going to be just an original function, it's going to be a family of functions. We will represent it by f of x. So we know, we have seen this same example earlier, so why don't we go ahead and simplify? The antiderivative of 4x cubed is x to the fourth plus sine x. The antiderivative of cosine x is sine x. And the antiderivative of 5e to the x is 5ex. And 7 over x will result minus 7 ln of absolute value of x. And then we will have plus c. And the condition, now at this point, we have infinitely many values waiting to appear through that plus c. However, now if we use this condition, don't forget we have this condition, f2 equals, f at 1 equals 2. F at 1 equals 2, right? The same condition, I wrote it like just by flipping the positions. But now why did I do that? Now don't forget, in the right side, you can compute this component based on the representation that you have. The meaning is this value that you have inside is the value, the corresponding value for x. Plug it in. Plug x equals 1, and then you're going to get 1 to the fourth plus sine 1 plus 5e to the 1 minus 7 ln 1 and then plus c. This ln 1 happens to be just 0. By any chance, if you do not recall such a condition, such a property, yet it's not going to harm, because you can see clearly this equation contains no x values anymore. You have just values. For instance, sine 1. You do not need to evaluate it specifically. This means sine at radian 1. We will just include it. And then e to the 1 is none other than e. You know the value. Approximately is 2.718. But we are not going to include any of them. What we are going to say is like the value of c. So 2 equals from this side 2, and from this entire side, the right side, it is just 1 plus sine 1 plus 5e, and then 7 times ln 1. That's just, this part disappears because it's a 0. And then you can have the value of c. Value of c is 2 minus 1, that would be just 1, minus sine 1 minus 5e. And now just plug this value in the original expression for the function, and that would be your answer. F of x equals x to the 4 plus sine x in the position of plus c, I'm going to have this entire term. So in most cases, you will get very nice round values for this, for pre-designed problems. But here, I just came up with this example randomly. This constant doesn't look nice, but it is just a constant. It's far better than having a plus c, because plus c can represent anything. Now, in this case, you have just a specific value. All right, let's proceed to the next step. Now, indefinite integral. What do we mean by the indefinite integral? It is just a notation. The title says just the same thing as antiderivative. All right, the phrase is not going to, it should not scare you, because it's just the same thing that we are already familiar with. The purpose of this simplification or this new notation is to have a better write up, right? So a better way of writing our expressions. So the way, just, I mean, compare this with what you had with d by dx notation in differentiation. We had d by dx. Of course, we knew this is not like a fraction. It is not just about canceling d with d. So it is just to represent the derivative with respect to x. The meaning of this component is the derivative with respect to x, and then you're going to feed function f of x, and you know what's happening beyond that point. You're going to differentiate and write down the answer right in front of that notation. Now, the same thing here, in terms of this, the meaning of the notation, think about this. Here you have this kind of a sign. It is called integral sign. And this part is called, it is just an identification of the variable, and it is formally called the measure of integration. Or I will just simply, for our purposes, I will say variable of integration. And what you're going to feed here in parentheses or right in front, sometimes even if you do not have parentheses, what you're going to feed in this blank will be the function that you're trying to find the antiderivative of. So in other words, what you're going to have here is a function, and that function has a name. We will call it the integrand. Integrand, because that is what we are trying to find the integral of. So we will call it integral, and that integral, in other words, now when we have this, look at this, this is the integrand. In other words, that is what we call the original function in this scenario. That's the original function. And what you see in the right side is the antiderivative. So simply what we're trying to have here is, other than saying like, given this function, compute the antiderivative, we're going to say like, we're going to just put it to this symbol and everybody knows what we're talking about. Now, a quick example. Look at this. Once you have this problem, the same problem that we have seen multiple times, right? We saw this problem. That is the very first example that we worked with. Now, other than writing f of x equals this and then find uh, the antiderivative, once I write down this, that means that equals simply this answer. And always it is an indefinite answer. Indefinite, in other words, there is a plus c to follow at the end. So compare. Now, the purpose of this entire notation is, now this comparison, compare this problem, the wording that I had to use for this problem and the wording I had to use for this problem. Here the notation says everything. Here I have to use extra wording, right? So that's exactly the meaning. So as far as you're familiar with the integration process, this is exactly, it's nothing new, right? So now integral formulas. Now, couple of things that we need to recognize. Here, first of all, when there is a power, this is called the power rule. The first one, x to the n. What is the integral? The integral is none other than, when you integrate x to the n, the answer will be x to the n plus 1. In differentiation process, we just reduce the power by 1 by bringing it to the front. Now here we are going to divide, first of all, raise the power to the n, power by 1, so it becomes n plus 1, and then divide by that exact exponent. Now if you do not see this, this is my recommendation. Just don't take my word for granted. Just take the derivative. When you take the derivative of this component, of course, we know plus c will disappear. It's a constant. When you take the derivative, this 1 over n plus 1, it is none other than a constant. You do not need to use the quotient rule here. N plus 1 is a constant in the denominator, so 1 over n plus 1 appears in front. And then take the derivative of this component, which is a power. When you do that, n plus 1 comes to the front because the power is brought to the front in the derivative form of the power rule, and then x to the whatever that exponent n plus 1, and then subtract 1 from that. That will result just x to the n. Now these two will get cancelled with each other, leaving just x to the n, and that is exactly what you are looking for here, right? The integral of x to the n. So that's how you can justify, in fact, this formula. It is none other than knowing the derivative and reversing it. So now, given that you're familiar with this formulation, or you're familiar with this integration process, now let's prepare just bunch of formulas just based on integration observation, just based on basic derivatives, the familiarity with basic derivatives. Now think about integration of a constant. We know when you differentiate x, when you differentiate this side, let's put it in that way. When you differentiate the right hand side, when k is a constant, and of course c is an arbitrary constant, so even worse with that. But now this will disappear. It's a constant alone, and then this one is a constant multiple of x, so k comes out, and the derivative of x is going to be just 1. So in other words, when you take the derivative, you're going to end up getting just k. So the meaning is, if you integrate just a constant k, that will result kx plus c. And if you integrate e to the x, that's going to be e to the x plus c. And this can be generalized with a very simple observation. If you have e to the kx, where k is a constant, I'll call this one constant. If that is the case, the answer will be e to the kx divided by k plus c, and this can be weaved in multiple ways. One simple observation is to just look at this and take the derivative. Don't forget, when you take the derivative, you need to employ the chain rule here, so there will be a multiple of k when you differentiate the inner function. So that will get rid of, that will cancel out the factor k in the denominator, leaving just e to the kx. And this formula would work when, only when k is not 0, because you put k in the denominator. So that is something known, e to the kx, and then the derivative of ln of x, more generally ln of absolute value of x, will coincide with 1 over x. Therefore, the integral of 1 over x is ln x. The similar way, when you take the derivative integral of sine x, now be careful here. In differentiation, when it comes to differentiation, when you take the derivative, you had just positive cosine x. But when it comes to integration, when you take the integral of sine, it will result in negative cosine x instead. If you do not see why, just take this one and differentiate. You will see when you differentiate, cosine itself will result a negative sign when you take the derivative, and with this negative sign, it will turn out to p sine x. And then integral of cosine is sine, and the integral of secant square is going to be tangent. These are none other than the direct reversal of the integral formulas, the position of the direct reversals of the derivative formulas. You've seen the derivative, so we reverse it. So with that, the last couple of applications, these are just inverse trigonometric derivatives. These are results of inverse trigonometric derivatives. So when you take the integral of 1 over 1 minus x square, you will end up getting arc sine x plus c. The result is coming from the derivative of arc sine x. That will result exactly what you see here. And then we do not have a separate formula here for arc cosine situation. The reason is this. For arc cosine, when you differentiate arc cosine, we know we will have just negative 1 over the same thing, negative 1, and the same thing is right there. So now this is just subject to a constant multiple. If you take it out, you can just employ the same formula other than using a different formula. Therefore, you do not need to have many pieces in this situation. Our cosine case is handled just by the same line. The same would work for these two formulas. So when it comes to the integrals of integrals resulting inverse trigonometric functions, you do not need to have a wider spectrum. You can just have three formulas to handle them. In some variations, this last result can be weaved in this way to enrich the application, the domain of application of the answer. So other than having absolute value here, you can put the absolute value there. So it is essentially again the same. We are using that scenario now. Both of these are the same pretty much. However, when we try to target something, an answer, we try to make it wide, as wide as possible. Other than having just simple x here, you can put absolute value of x there, and you can just reduce the restrictions of the starting point of the problem. So now, given these formulas, and this is my recommendation, do you recall what you did for derivative formulas? You had one page of derivatives, and you had uh, just after the derivative formulas, you had rules. You had all of them in one single page. My recommendation is you to do the same with integral formulas that you see here, together with these two rules. These two rules are again the linearity properties direct resulted by linearity of derivatives. When you take the derivative, we know we can split it over a summation or subtraction. That is how we get this result. And then a constant multiple will always pull outside of the operation that is still valid for integration. Now, you can have all of these results again, all of these results, like let's say the rules and the formulas, fitted into one page. Have it accessible. The purpose is for you to see two things. The first one, all of these are results from the derivatives, results of derivatives. So that simply means you're essentially writing down the derivative formula sheet in a flipped way. You flip it. That's why I told you the key essential component is the derivative in this conversation. Once you have it, Now, once you prepare this, when you compute integrals, you can easily access, you can easily organize your thoughts when you directly see the integral. That is the second purpose of having such a write-up. So now we do have two items: the derivative formula sheet, integral formula sheet. Let's prepare them. This is not to use them in an assessment. This is just for you to summarize how uh, how simple or how much we can compress what we've learned. Essentially, we've learned only 2 pages worth of stuff. The rest is about the skills that the way that you're going to use them in different computations. All right. So, right, starting from this point, now let's try to work with a few examples. Now, the starting step. Why don't we do this? Other than just looking at a solution right away, example number one. Look at this. A problem. Now, integration could be really interesting in certain aspects, in certain ways, because sometimes, since not only sometimes, like it's like always, since integration is a reverse process, we are trying to walk backward, right? Sometimes it is very complicated to see where it started from. It's very complicated to recognize it. Even for very simple functions, like let's say if you write a random function, you can find the derivative mostly. It's like always, it's possible as far as the function is differentiable. However, when you write a very simple function like with really simple extensions, yet you will get a very challenging situation. You could end up getting a very challenging situation in integration. However, this example is not such, but once you look at it, you may have you may see a couple of things. Oh, are we going to take the integral of the top and the bottom separately? Can we do that? We know how to take the derivative integral of the top. It's just a polynomial, and we know how to use integration, just the power rule, and we know how to use the power rule in this case. Now, if your thought process is in that way, think about this. When you take derivatives, there was no simple formula for a quotient when you have a function divided by a function. That came with a little bit slightly complicated formula called the quotient rule itself. So you just did not differentiate the top and the bottom and then divide them out. So that's exactly what you need to understand here. If you did not have such a simple way in differentiation process, there is no miraculous way to get such a simplicity in integration. So don't do that. If you did not see any formula for that, don't use formulas. Instead, think about simplification. One simplification that you can have is to separate the fractions, right? Once you separate fractions, you can see exactly how it's going to work. And when you simplify, now you can see how each component would work. And then x squared over x, it's just simplified. It's none other than just x. And then along that line, once you get to this level, now you can integrate it directly. And sometimes, like having this plus c, it is essential. If you forget that plus c, if you tend to forget that plus c, have it like a smiley, just have some kind of a reminder. It is essential, right? Put a smiley, right? Smiley face, something. Otherwise, if you if you miss that, your answer would get creepy. So do not let that happen, because sometimes it gets creepy and it gets spooky in mathematical sense. Don't let that happen. So make it funny, just to make sure that it's not going to be forgotten. All right. Example number 2. Let's again start just by looking at it. Pause and think about it if you do not see it right away. All right. I hope you gave it a thought. Now, this can be converted. The square root of x is none other than a power of x. 1 over square root of x is again that Square root being a power, the exponentials, this can be translated. So this is what you see right here in the process. X to the 1/2 and then x to the negative 1/2, and then you use the power rule. When you use the power rule, don't forget x to the 1/2. Now the power rule itself is x to the n. X to the n is integrated will result n plus 1. Sorry, what did I write? X to the n plus 1 over n plus 1 then plus c, right? And then you do not need to have plus c for each component when you take the integral, 1 plus c for this and 1 plus c for that, because at the end it's going to be an arbitrary constant no matter what. So you will have a 1 cumulative plus c at the end in your computation. So now look at this. Raise the power by 1 and divide it by 1 n plus 1, the same exponent. So that's what we did. X to the 1/2, 3 to the it's 3 over 2, and then 3 over 2 here, right? So the same situation here, because negative 1/2 is here. If you add plus 1, it becomes positive 1/2, and then you divide by exactly the same component. So this is what you get after the simplification. Here I did some simplifications because 3 gets cancelled with 3, and then the denominator has this component as again a fraction. A denominator of the denominator comes to the numerator, so that's why you see this. So you can think about the simplifications in that way. And then the next example, pretty straightforward, it's nothing new. 5 cosine x 7, this is potentially the easiest in that combination. Example number 3. Example number 4. All right, so again, give it a thought right here at this point. Sine x divided by 1 minus sine squared x. What would you do in this scenario? This can be, once you have 1 minus sine square, don't forget, that is none other than cosine square. We have seen this many times in trigonometric computations, and this is starting from the starting step of trigonometry, basically, that is none other than the Pythagorean identity. So 1 minus sine square is cosine square. But now this may seem like little complicated. How are you going to integrate sine x divided by cosine square? Sometimes it's about representing it properly. Sometimes you need to simplify. So in this process, you may need to have some inspection. You need to just think about it. If you separate two copies here into two pieces, one cosine separately, and if you separate them into fractions, this turns out to be sine over cosine is nothing other than tangent, and 1 over cosine x is none other than secant. So now let's write it tangent times secant, which is none other than secant times tangent. Wait, do we have a formula for that? Yes, of course, we know the derivative of secant. That happens to be secant times tangent. Therefore, the answer is right in front of you. So now, some of these computations could be like, it need not to be straightforward. You may need to write it. You may need to do some experiments. In mathematics, you can do experiments. You must do experiments in mathematics. In mathematics, we are not going to uh, have expensive apparatus, any equipment for our experiments. Instead, we are going to use pencil and paper, right? We can just write it down and see what kind of approaches would work, what would not work, and we have a set of rules to follow in mathematical computations. That's all. As far as you're within the collection of rules, you can have different possibilities. You can think about that. That's exactly what I did here. I did not have a clue right at the beginning. Then I just convert it to a certain form, which is kind of obvious starting point. And then I couldn't see where I'm heading right here. And then I wrote it in a different form so that I can see it better. And then I got to that point. All right, one more example. Now, this should be straightforward. Now here this says f double prime. F double prime is given with two conditions. F prime at 2, if prime at 1 is going to be 2, and f at 0 is going to be 3. Two conditions given. And what we need to do is to find the original function. Now, think about this. When you're given the second derivative, the second derivative is the derivative of the derivative. So this is the second derivative. So since it's a second derivative, now this is what we are going to do. First of all, we will find the first derivative. To get to the first derivative, we need to integrate it one time. So let's have line number 1. F prime x is none other than the integral of the originally given function, which is none other than the second derivative. So now when you take the integral, don't forget, it is none other than just the power rule. You use the power rule and you end up getting 3x square over 2 and then plus x in the position of 1. When you integrate 1, it becomes it becomes plus x. And then you have a constant. Instead of writing it like c, I will call it like, let's call it c1. Because in this process, you're going to see two constants no matter what. Now, once you have this, this is what we can do. Don't forget, we do have a condition given for f prime. Now, if you utilize it, that condition is none other than 2 equals f prime evaluated at 1. Now I'm going to evaluate this right hand side when x equals 1. When I do that, this is what I end up getting. And don't forget, all of these are just numbers that I can evaluate. Now do the evaluation. C1 turns out to be just negative 1/2. Take a moment to do that properly. And then, now once you have that value, this is what you can say, this is what you can do, bring it there, plug it in the position of C1, and then let's have the refined version of that function. This is what it looks like. The next step. Don't forget, we still have f prime on our hand. Our goal is to have the original function f of x. So what you need to do is to integrate this one more time. When you integrate, you can see 3/2 here is a constant multiple. So leave it in front. Integrate x square. So that will result x cubed over 3. And then plus, here you have x square over 2 as the integral of x. And then integral of 1/2. It's a constant, so it becomes negative x over 2. And then plus c2. And then the C2, now why did I call it C2? Because already I used C1 in the context. So you can use one of them to be just C, the other one, even if you use C in both places, it's not going to be a problem as far as you have a clear idea which place holds which variable. However, right when I have this, now I'm going to evaluate it by using the second condition. Don't forget, the second condition is right here. Look at it, remember it, f0 equals 3. So now I'm going to utilize it. 3 equals f0. This means plug x equals 0 in the right hand side of this expression, and we're going to get all zeros at the beginning of that term, leaving just only c2 in the right side. So c2 equals 3. That's all we end up getting. So that's what we have here. And once you have it, this is what you're going to do. Bring it over in the position of C2. It's right here. and then write it down and pass it again to one last step to write down your definite finding, definite answer right there. So that is exactly how you can iteratively think about this process when you consider a repeated application of differentiation and about reversing it. So that brings us to a conclusion, the conclusion of this lesson. And what we did here is to identify the next important half, the important component of calculus, the story of calculus. We started the journey of integration. However, we started the computational aspect, which is called the anti-differentiation, or we call it precisely like, let's say, in integration language, we will call it indefinite integration. We build up a bunch of formulas, and all of them are resulted by direct differentiation formulas. So it is nothing new as far as we know how to do the derivative. Now we are thinking about doing the reverse computation. And eventually, when you earn more familiarity with these topics, you need to recognize efficient ways of doing these computations with more sophisticated tools on your hand. And that is the journey of calculus ahead. For now, make sure that you fluently use your derivative knowledge base to work with these problems, and the formula sheet that you prepared for this particular lesson is going to be helpful, because other than just recalling a derivative, now once you're familiar with integration as integration itself, you can self-contain it when you work with problems. All right. So with that, we will conclude this lesson, and we will um, meet in our next lesson. And until then, I wish you a wonderful time.